Welcome to the deep dive. It's late, the servers are humming quietly, and if you are anything like us, this is exactly the time your brain wants to solve an architectural puzzle.
Yeah, it really is the perfect time to get into the weeds of system optimization.
Exactly. So for you listening, especially those of you who spend your days deep in code thinking about scaling and system optimization, we are looking at a stack of research on a paradigm shifting concept today. It's called mixture of experts, or MOE.
Right. And the core mission here, the sort of golden rule we are going to explore, is this idea that not every neuron needs to fire.
Which sounds incredibly counterintuitive at first. But before we get there, let's just quickly recap the journey, right? Over previous deep dives, we assembled the foundational building blocks of the transformer architecture.
We did, yeah. We went through the attention mechanisms, which,
Yeah.
calculate context, and the feed-forward networks, the FFNs.
Right, and we also covered normalization and positional encoding. All brilliant foundational pieces.
They are, but what we're talking about today, the MOE layer, it feels much more like a clever engineering trick.
Oh, absolutely. It's the kind of trick that software developers specifically will really appreciate.
Right, because to understand why we need it, you really have to look at the brute force of the standard dense transformer.
The baseline problem, basically.
Exactly. In a standard transformer architecture, there is this massive bottleneck. Every single token you feed it has to pass through every single parameter in the model.
Okay, let's unpack this for a second, because for you listening, this sounds entirely crazy. It's like running an entire massive code base's test suite just because you changed one line of CSS.
That is a great way to put it.
I mean, isn't that just a wildly inefficient use of compute? Like, why run the database teardown tests for a simple padding adjustment on a button?
It is wildly inefficient. And that brute force approach, well, it becomes a massive, massive hurdle as these models scale up.
Because of the hardware limits, right?
Yeah. Yes, exactly. You hit the memory bandwidth wall. You physically cannot move the data fast enough from VRAM into the compute cores if every parameter has to be read for every single token.
Wow. Which perfectly sets the stage for why not every neuron needs to fire is such a crucial breakthrough.
Right, so since hitting every parameter is inefficient, how does the model decide which parts to use? That is where the MOE routing mechanism comes in.
Enter the router.
Enter the router, exactly. The source material uses this really helpful analogy. Think of the router as a triage nurse in an emergency room.
Oh, I like that.
Yeah, so when a token arrives at the MOE layer, it's like a patient walking into the ER. You don't make all 500 doctors examine the patient at the exact same time.
Right. That would be total chaos.
Complete chaos. Instead, the triage nurse quickly glances at your symptoms, makes a rapid assessment, and decides which specific doctor you actually need to see.
So if we connect this to the bigger picture for our listeners, the router is essentially acting like a highly intelligent load balancer.
Yes, essentially a layer 7 load balancer.
But instead of routing traffic based purely on server capacity, like a standard round-robin setup, it's routing based on specialized domain expertise.
Precisely. It inspects the payload, which, by the time it reaches this layer, is a dense mathematical vector, and it produces scores for each available expert.
To make this abstract concept a bit more concrete, let's actually look at a real-world implementation.
Let's do it. Mixtral 8x7b is the perfect case study to show where MOE becomes, well, basically magical.
Yeah, the specs on this model are just fascinating.
They really are. So in Mixtral 8x7b, instead of a single standard FFN layer, the architecture has exactly 8 distinct experts per layer.
Okay, 8 experts.
And each of those individual experts is roughly the size of a 7 billion parameter model's feed-forward network.
Wait, hold on. Here's where it gets really interesting. If we have 8 experts, and each one is the size of a 7B parameter FFN.
The total parameter count must be enormous.
Exactly. We are looking at an incredibly heavy system overall. So how does having a massive total parameter count align with the efficiency we literally just talked about?
Ah, well, that is the genius of it. The total parameter count is indeed high. It's about 47 billion in total. But thanks to the router, only a fraction of those are actually activated.
Oh, I see. Because it's not using all 8 at once.
Right. It uses what's called top 2 routing. For any given token, the router only selects the top 2 highest scoring experts.
Making the other 6 stay completely dormant?
Exactly. Plus, the attention layers are shared across all the experts. So you keep compute costs down while maintaining this massive high-capacity knowledge base.
You get the intelligence of a massive model, but the inference speed of a much smaller one.
You got it.
Let's put this whole system into motion. I want to trace a single piece of data through the layer so we can really see this.
Good idea. Let's track a single token.
Okay, let's use the word mitochondria. We'll say we pulled this directly from a passage in a biology textbook we are feeding into the model.
Perfect. So mitochondria arrives at the MOE layer as a rich mathematical vector full of context.
Walk us through exactly what happens when mitochondria hits that triage nurse. Like, how does the router score a highly specific biology token compared to a simple word like the?
Well, the router does a rapid matrix multiplication to examine the vector for mitochondria. It checks its learned weights and scores the 8 available experts.
And because it's a biology term, it's going to find the experts that organically specialize in science, right?
Yes, exactly. Let's say expert 3 and expert 7 score the highest
Wow.
because they adapted to structural relationships in biology. The router dynamically activates just those two specific FFN experts to process that context.
Leaving the rest of the layer completely dormant.
Not a single flop of compute is wasted on them.
That's incredible.
But then on the very next token, say the word is, the router inspects it and finds entirely different features.
Because is just structural grammar. It doesn't need a science expert.
Right. So it scores expert 2 and expert 8 highest because they became the syntax specialist. The biology experts go idle and the syntax experts wake up.
It's just a synchronized dance. Token by token, fraction of a second by fraction of a second, the routing pathways shift.
It is dynamic routing at a massive scale.
So, summarizing this core aha moment for you listening, understanding scaling in AI isn't just about building bigger, denser blocks of compute.
No, not at all. It's entirely about clever dynamic routing. It goes back to that rule. Not every neuron needs to fire.
Exactly. Well, we have covered a lot of ground tonight, but I know you have a final thought to leave everyone with.
I do, yeah. Something for you to mull over. If the entire efficiency of this system relies on a router acting like a triage nurse, making split-second decisions based on a quick glance,
Yeah.
what happens to the model's understanding if that triage nurse slightly misdiagnoses an ambiguous token, sending it to the wrong expert entirely?
Oof. That is a brilliant puzzle to end on. A subtle hallucination purely from a routing error. Thank you so much for joining us on this late-night exploration into the architecture of modern AI. We will catch you on the next deep dive.